The first step is to open the file containing the morphological tracing. To do this, we click on the Open button and select the desired file. In the tool we can see the loaded tracing as well as an approximation of the neuronal membrane. The appearance of the visualization can be modified in the View panel, where we can change, for example, the color of the neuronal membrane, or its transparency level. In the visualization it is possible to select the different nodes that compose the path and, once selected, it is possible to modify them. For example, we are going to move a node to place it close to another one. An alternative way to modify the selected nodes can be found in the Edit panel, where we can see the 3D coordinates of the selected node as well as its radius. To modify the radius, we must edit the value in the box and click the Apply button to make it effective. In case the Auto Apply option is selected, then any changes in position or radius will be reflected automatically, without the need to click on the Apply button. Nodes can also be selected in the Select panel that shows the morphological elements arranged in a hierarchical fashion. This hierarchical representation is linked to the visualization, and any change in one of them will be reflected in the other. Colors in the hierarchical view represent the selection status, so that the blue text indicates a partial selection, as in the case of NeuroEditor 5. A blue background indicates a full selection, as in section 53, where we have just selected all of its nodes. It is important to note that both representations are linked, and as we can see, the selection in the hierarchy updates the visualization and vice versa. If any modification occurs at any of the tracing points, the neuron membrane will be updated in real time. In addition, if the modified node is the beginning of a NeuroEditor, a new approximation of the soma will be computed. To exemplify the automatic error detection, we are going to generate two errors. One of them has been previously generated by leaving two nodes too close to each other. Let's include a second error by moving a node, so that the dendrite trajectory undergoes an abrupt changes of direction. To take advantage of the automatic error detection, we will make use of the Correct panel. The first step is to add the tests we want to run. In this case, we select oversampling and angle smaller than 90 degrees. As can be seen, each test has a series of default options, where we can select to check the error manually or to apply some automatic correction actions. In our example, we will select an automatic correction when an oversampling is detected, by automatically removing the unnecessary nodes. In the case of sharp changes in the trajectory, we will correct the errors manually. As can be seen, one of the two nodes that were intentionally placed too close together has been removed, while the second test, an error at node 381, is reported. By clicking on the button, the erroneous node is automatically selected and centered on the screen so that it can be easily located. To assist the user, the drop-down menu shows different automatic correction options. Once the node has been modified, either automatically or manually, its button will appear in green. Another feature of the application is the possibility to simplify the tracing in the Edit panel. A set of automatic simplification methods are distributed, so that the user can reduce the number of nodes that define the tracing. Now we are going to simplify the tracing applying nth point simplification algorithm, setting the adjustable parameter to a value of 2. This means that 1 out of 2 nodes will be removed. By setting a higher value, we get a much more aggressive simplification. In addition, the user can also implement his own Python script to run a custom algorithm and process the tracing according to his needs. In this example, we are going to assign an equal radius to all the nodes. With this example, we end up with an extremely simple tracing that reflects the branching pattern and the lengths of the segments, ignoring the curvature and thickness of the branches. We could export the generated neural membrane, as well as the modified tracing, and use it in another 3D meshing program, allowing us to calculate metrics such as area, volume, etc.